My name is Christopher Maxey. I work for BAE Systems, Fast Labs we call it, which you might think of as kind of the advanced research arm of BAE Systems. A couple things that you need to know about me. I'm a hardware guy. I'm an RFIC guy. So I don't want to seem like I'm coming out of left field, but it might be a little bit of a non sequitur, this talk. It is a very hardware-centric talk. But I do want to introduce to you what I believe is a very important, I don't know, dare say, game-changing capability that I want this community to take advantage of. The second thing is that I work for a DoD contractor, right? So why, you're asking, is some stodgy, tie-wearing DoD contractor type coming to GRCon, right? And 2 years ago, I probably would have asked the same question, right? I probably shouldn't be here. But we all know that the world is changing very rapidly, and the DoD is seeing the advancements in machine learning, artificial intelligence for RF. We're seeing increased relevance of SDR for DoD missions, and we're seeing also increased relevance of open source for DoD missions. So to be honest, people like BAE Systems may be late to the party, right? And I would hope that starting now, we have a more continuous engagement with this community, right? Not only to learn, because I think obviously this is a community of innovators. I think there's a lot to be absorbed from you to me, right? But also to show you cool stuff. And without further ado, I want to introduce you to one of my cool things, right? Which is the matrix technology and the Hedgehog SDR, right? So non sequitur number 2, this is not Hedgehog. But I do like this picture because it does highlight my chip, which is here. We called it a matrix RF FPGA. And it does show you the kind of capabilities that it enables. This is a 1.5-inch diameter SDR that has 8 channels on it, transmit, receive, up to 20 gigahertz, right? So that's the kind of thing that our company does, right? So go through the FPGA, the RF FPGA. I'll introduce that concept to you. It is potentially foreign, maybe exciting, maybe interesting. I hope to gather you to my side once you've seen this. And then introduce this module, of which, of course, this is not an operational one, but I can show you pictures of real ones. This is a dummy one. And then do a very brief demo. Now, it's going to be the simplest flow graph you've ever seen at one of these conferences, but the idea being that I am introducing you to this. This is the tip of the iceberg type of thing, and I really want the community to start taking advantage of what this hardware has to offer, right? So this is my palette cleansing chart. This is trying to get us all on the same page. They're much busier after this, I promise you. Right, so what is an RF FPGA? It sounds like something I just invented, which quite frequently I did. It should save you time and money versus a digital ASIC. If anyone has designed a high complexity digital ASIC, you know how much they are, you know how much they cost. So let's prototype, just as you do in an SDR at the board level, let's prototype in the ASIC and give you ASIC level reprogrammability. Rapid prototyping, I don't need to stress to this community why that is important, why that is interesting. And also in-field upgrades, right? So the DoD has an incredibly bad track record for upgrading their technology. You'd be appalled to know what processor the F-35 uses, right? You think of the F-35 as a brand new plane. You would be appalled to learn what processor is in that plane, right? And on-the-fly response to the environment, right? So as everyone has access to 5G technology, as everyone has access to these rapidly reprogrammable ASICs, how do I respond to them? As a BAE Systems, as DoD contractor, that is my job, right? Okay, so where are we and where did we come from? We started this program. It's a DARPA program. If I haven't mentioned that, I apologize. That started back in 2013. We are through we're on a program right now that we call Hedgehog that is developing the 4th generation of what we call the matrix chip. So I'll go through the salient characteristics of this as I go through, but I did want to give you kind of the family portrait to where we're at. What's most important is that we are 8 channels, 4 transmit, 4 receive, on a chip, up to 40 gigahertz, in a single 8 by 10 millimeter die, okay? That's what that single chip will do. And I'll go through all the pieces of this as I go through. And hopefully, as I go through this, you start realizing what you could do, right? Because that's the point of this. It's not for this is not just a poll exercise. I want to tell you, I want to get you thinking, get you engaged. All right, so this is a block level diagram right? So if you know anything about FPGAs, they're a collection of LUTs, they're a collection of memory, ultra-RAM, you name it, all connected by an eminently reconfigurable fabric. And that's precisely what we're doing here. The scale is slightly different, obviously. RF components are far larger. VCOs are far larger than you're going to find in a 7-nanometer Xilinx FPGA. But at the same time, the concept is the same, right? We have 10 blocks in the V4 architecture that I'm not going to talk about now because it's, we just taped it out. This talk will focus on what I'm calling the V3 architecture. 10 blocks. We have direct down conversion receivers that go from 0 to 6. We have block down converters that go from 6 to 20. And we have 2 PLLs that go from 0 to 20. And they are eminently reconfigurable. And I will go through some examples on how you might use this, how you might reconfigure this, right, as I go through. All right, some more salient characteristics. All right, you can do direct conversion or receive. You can do direct conversion transmit from 0 to 6. We have an in-path receiver. That's what this green block is. You can do Superheterodyne RX, receive, transmit. Coming in at, say, 18 gig, down converting to 5 gig, and then going straight to the direct conversion receiver. You have control over that entire frequency plan. IQUp Converter, RF transceiver. It can even operate as a mux-demux, a signal mux-demux, depending on what you want to do with the signals. In each block, you have reconfigurable instantaneous bandwidth from 10 megahertz to 2 gigahertz. You have gain, it's actually 50 dB. So 0 to 50 dB programmable gain in every block. Programmable linearity versus DC power consumption. So in certain circumstances, you may be weighing power consumption over the linearity of your chip. Center frequency, like I mentioned, 10 meg to 20 gig. The essential piece in V4 is that we are pushing that to 40 gig. And slightly above 40 gig, to be quite honest with you. And integer in/fractional n PLLs. With on-chip programmable filters. Okay, and you program this with a SPI bus, just as you would many of the other chips that you may already be familiar with. And it has distributed on-chip memory so that you can set some of these states and reconfigure the chip to, like I said, near limitless reconfigurations in as few as 10 nanoseconds. So that is the rate at which you can swap between an 18 gigahertz super heterodyne receiver to a 4 gigahertz direct conversion receiver. Okay, kind of go into the blocks one by one. I won't bore you too much with it. I'll go quickly. I don't have a lot of measurement data here. I knew that you were more interested in the top-level application of this, not so much what it can do. But if you have any questions on what it can do specifically, please come to me, find me, let me know. All right, so this is a direct conversion receiver on a chip, and we have 4 of these, right? So this goes from 0 to 6 gigahertz. It has, like I said, programmable gain, programmable linearity, and also programmable filters on both the output and the input so that you can notch out signals of interest, or signals of non-interest, I suppose. And you can also tighten up your baseband output. This is IQOut, so all of the filtering here is done in baseband. But with the in-path filter concept, if you're not familiar with that, in general terms, it converts a low-pass filter up to RF for you so that you get the advantage of an RF filter, but done at baseband. All right, what does this block do? This is my block down converter. So if you're above 6 gigahertz, and the green block that I just showed you in V4 goes up to 10 gigahertz. So you can do X-band all the way to X-band and direct conversion in V4. So in this version of the chip, though, you would be down converting anything between 6 and 20. Right? In the future version, you would be down converting anything between 10 and 40 down to a IF that you can then ingest with the RF baseband block. All right, so this is, you have 4 different ways to do this. You can do microwave in, microwave out, just simply use it as an amplifier, or you can use it as a mixer. So we call this our mix or amp. It's a mixer or amplifier. It's one more control feature that you have inside the chip to do massive reconfiguration. All right, and finally the PLL. All right, this is 0 to 20 gigahertz integer in and sigma delta fractional n PLL. You have 2 of these, right? You have 4 of these in V4. The idea being that if you have a certain frequency plan and you know that you want to hop rapidly between different frequencies, you can do that in as little as 10 nanoseconds. Right? So that is your hop rate. And you can also export these LOs to other chips. You can import LOs from other chips. You can import all the way up to 325 megahertz reference frequency into these PLLs. So a myriad of things that you can do. All right. So here is the dive photograph and how you might route signals. The only point that I want to make here is that you do have significant access to this chip, both with LO, RF, and microwave, both in and out. All right, so as I go through this, it kind of gives you a rapid-fire idea of different things, different applications, different configurations that one might put matrix into. All right, so this is a 2-channel DC to 6 gigahertz direct conversion receiver. You're coming in 2 baseband blocks to get an additional level of filtering, because every level of filtering that you do adds 2 orders to your filter. Right? This is a 0.5 to 20 superheterodyne. So you're going above 6 gigahertz, you're coming in, you're doing superheterodyne. So now you have the flexibility to do either superhet or direct conversion, depending on what your applications require. This is doing an increased gain and filtering. You need that increased gain to close a link budget. You can go through additional blocks, right? So hopefully you're getting an idea that the palette, right? So I'm trying to give you a palette. You can create near infinite things with that. Right? And here's a signal mux, right? So this is 2 to 1. I have 2 signals coming in. I multiplex them onto a single line, and I go out. I can do more things with that. I can do microwave amplifier and up converter. So if you have a frequency coming in at 10 and you want it out at 20, or if you want it out at 40 in the next version, here you go. If you want dual IQUp Converter, simply want to come in and do baseband to RF, certainly something that you can do. And this is a DC to 6 gigahertz RF transceiver, right? So just another way to do transceiver operation. And this is a more complex one where you say, I've got one signal coming in, and I can turn that to 12 different signals going out. And I can amplify each and every one of them, right? So, and this is a 8 to 1. So now I've got 8 signals coming in, and I want to multiplex them all to 1, right? So hopefully that gives you an idea of the flexibility of the chip. I certainly couldn't have done all the things. It's got more than 260 reconfigurable bits. So 2 to the 260th different configurations. It would have been here for months, right? What have we done with it, right? So the chip itself is useful to me, potentially not useful to many of you. Really, I mean, it's kind of by itself not so useful. What we did on this program, the early program, was we integrated it with a National Instruments X310. Right, so this is where we start saying, here is an SDR. Right? The chip is one thing. It's a tool in a toolbox. What we try to do now is enable a real software-defined radio. And the first thing we did was say, hey, Edis has this great platform, the X310. Let us use this as its front end. All right, so we built what we call the matrix evaluation kit, which is a matrix chip inside this daughter board. We wrote custom GUIs for this. I'll point this out as being what I call the expert level mode, where you have access to literally every bit. Right? So you have this GUI control. It's controlled via USB. It's controlled the USB to SPI. And then you integrate that with an Edis X310. Right? So National Instruments has been a great partner with this, Edis. Right? And so that started what continues to be an evolving relationship with National Instruments in an attempt to get this out to those who might use it, right? Just to show you kind of where this fits into this ecosystem. So once we're there, once we are in that box, we can leverage the ADCs, the DACs, the FPGAs, and GNU Radio, right? Now we're plugging into the infrastructure. Now we're plugging into the folks that can really use this, right? Okay, so that's the chip, right? And I've also shown you a way to use the chip. And we have several MEKs kind of floating around. The Navy has them, the Air Force has them, several folks in the government have them, right? And so that's kind of how they're being evaluated now. So how might they be evaluated in the future, right? So this is kind of step 2. I showed you one chip, I showed you one module, and I showed you the X310, right? So what's kind of next, right? And so what we're doing on the Hedgehog program, which is sponsored by Tom Rondeau, you may have heard of him. He is funding us to combine the chip that I just mentioned, that I just introduced you to, which is over here on the left, with an UltraScale Plus Xilinx RF SoC. So if you haven't heard of the SoC, RF SoC, it is a Xilinx UltraScale Plus FPGA that has it's a quad-core ARM A53, plus the programmable logic, as you might expect, since an FPGA, plus 16 ADCs and 16 DACs, all monolithic on the same chip. Right? So now what you're looking at I know you'll see the picture and it's more than 2, but what you really, core functionality is 2 ICs, 2 SoCs. You have the matrix chip, which is 1,000 different RF transceivers, plus the RF SoC, which is PL, programmable logic, processing system, plus ADCs and DACs, right? 2 chips, right? Okay, so what does that look like in block diagram? All right, so this is the matrix V4, the chip that I just mentioned in a slightly more abstracted view. This is the Xilinx RF SoC. And here's what we call the personality connector. Now, I won't go too much into detail there, but there is an option, say that you want superior noise figure at a certain band, and you want a band at LNA, at say L band or S band or C band or X band, then you would augment this with an external chip. Or if you wanted more output power at say C band or KU band, you would put a PA at that band in this, and it connects to what we call a personality connector. We're personalizing matrix for a specific application. But these are plug and play. You would stay with the same module and then come in with different RF, right? Okay, so this is what the board looks like. I have it here. This is not really good for passing around, but it's, you see the dimensions here. 4 matrix chips, which are highlighted here. On the digital side, we have the RF SoC. We have 4 Firefly connectors, which go to the GTYs on the RF SoC. So aggregate bandwidth is something upwards of 380 something gigabits per second. DRAM, external DRAM, there's QDR, there's NOR flash, there's NAND flash, all the things that you might expect in an evaluation kit that you get from Xilinx, but all on this SDR. Right? So this is a 16-channel SDR. And this is that personality card I mentioned, right? So one of the key criticisms potentially with the DoD is that everything is so very expensive, right? So we spend $50,000 on hammers, right? So I will tell you that this is not necessarily the cheapest thing that you'll run across, although it's cheaper than the hammer I just mentioned. But we have a range of things that we have built and are designing based on this core platform, right? So this board came back in July, it's like mid-July, but we expect and we are certainly building on that product platform all the way down to this form factor, which is an Arduino, right, that has 1 matrix chip on it, right? So the idea being that you have this kind of massive solution to solve a lot of problems, right, and go into array applications, MIMO applications. If you don't need that many channels, or if you're simply looking for a prototyping platform, then there's this available as well, right? So a wide range. And in between, we have 3 UVPX versions. We have a 2X version that has 8 channels instead of 16 channels. So we're kind of filling that gap, right, with that kind of hardware. All right, so how do you program it, right? So this is where I start to speak your language, right? And so hopefully I translate well. So this is kind of the state where we're at. Like I said, we got hardware back in July, and we were running Linux on the board 2 days later. We are gradually getting the infrastructure together to make it so that you can have access to this on the software level, right? So what we do now is we have GNU Radio running on PC, as you might expect. We convert that to a custom kind of proprietary, although it's not necessarily proprietary. We could certainly open that standard SEO file. And this goes over gigabit Ethernet to the Xilinx RF SoC, which then arbitrates programming of the matrix die, right? And then on the chip are these ADCs and DACs, which are nominally running at 2 gigasamples per second each. And recall that we're doing IQ, so that's 2 gigahertz of instantaneous bandwidth per channel, right? So there's potentially 16 channels of 2 gigahertz of bandwidth, right? But right now, what you'll see in just a second is that coming back over gigabit Ethernet. So we're fairly limited in our bandwidth now. But eventually what we hope to do, and we're working with National Instruments to do this, they have some representatives here in the room, is to get UHD ported over to this architecture, to get the RF NOC ported over to this architecture. So once you have that, we start becoming more integrated with your ecosystem. And then we'd be doing 2 times 10 gigabit Ethernet back to the PC. So this looks a lot like what you're capable of doing with existing Edis products, but just with the flexibility and the extended frequency range that Matrix offers. All right, and then what do we do after that? Well, what do we do after that is we have another program going on at DARPA that is implementing a VITA 49.2 interface so that you can control Matrix with standardized control messages. Not only center frequency and bandwidth, those are the kind of the germane, benign things, but also say beam width, beam steering, as you connect this to a phased array radar or a phased array receiver. So we're also going 2 times 100 gigabit Ethernet, because like I mentioned, you have 8 receive channels running at 2 gigahertz per, 2 gigahertz. So that's a lot of data. These are 12-bit ADCs. So that's a lot of data, right? And so we'll pull that over with 2 times 100 gigabit Ethernet, right? All right, so that's the hardware, right? Now, what I have here is a couple videos on what we've been able to do just in the past couple weeks, getting this running up on GNU Radio, right? So what I want to stress, though, is that this is kind of what I would call the beginning, right? So we have a control infrastructure interface to this chip on this board using GNU Radio. We will soon be doing that through UHD. We will soon be using RF NOC. And my hope is, with Tom's blessing and as we can get these things out, try to see what the community can do in addition to what I'm about to show you, which is fairly, it's more like a first light kind of demonstration, right? So the idea being that we have this new GNU Radio block, right, that allows you to configure many of the things that I just mentioned, but not all of them. Right, so we've kind of abstracted away some of that nuance to give you control over the more salient characteristics, right? So center frequency, the LO frequencies, the whether or not you're doing homodyne or heterodyne, how you are routing signals through the chip. Right, so this is available through this block. And as I mentioned before, this is a very simple flow diagram. This is not to extol the virtues of this particular flow graph. But it is to show you that we have this block available, right? And then the thought being that once you have it, you start integrating that with your demonstrations using this hardware, right? So the very first thing that we did, of course, was simply make sure that we could get data out, right? So like I said, first light demo. We are setting up one of my PLLs to be the input frequency. So I'm not using an external source. I'm actually generating my own frequency, and I'm down converting it. It happens to be an IF of 200 megahertz, right? So you can see this signal coming through, right? So we have verified that the RF works, the ADCs work, and you can get data in and out of the chip onto the PC, right? What's the very next thing that you might do? Well, why don't you change the frequency, right? Right, so we have it running. You can change the frequency on these sliders, as I'm sure you're very familiar with, and all of a sudden your IF is moved 100 megahertz, right? Is this the most overwhelming demo you've ever seen? Absolutely not. What the point is, right, is that the hardware is in hand, the software infrastructure is evolving, and I want to engage this community to see where we go with it, right? So for DoD purposes is one thing, but for commercial purposes, maybe quite a different thing. For radio astronomy, quite a different thing. That's kind of the point, right? That's kind of the point. So I hope I've engaged the right community for that, right? So in closing, just wanted to say thanks to a whole bunch of people. Tom, obviously, and his team over at DARPA. AFRL is also a sponsor of this program. Jazz Semiconductor, which is our fabrication agent for the chip itself. They're a fantastic organization to work with if you're ever doing RFIC design. And the guys at NI and Edis Research. So that's the talk. Appreciate the time.
Okay. On time. We have plenty of time for questions, actually. I'm sure we have plenty. Okay, there's one over there. Actually, can I see some hands so I can schedule a little bit? There's only one? I don't believe that. I have questions. And who's the other? Where's the other microphone? Perfect. Okay, Dan.
This is awesome. So when will this be available commercially?
Okay, so
who will be making it? How much will it be, and how much power does it draw?
Okay, so there's a lot wrapped up into that, right? Okay, so I'll unwrap it as I answer, right? So the product, we have what we call alpha, right? It's not a very sexy name, but it's the very first board off the line. We have these. There's 5 of them in existence. Right, so as you can imagine, they're prototyping. We're hammering on them. They're breaking them as they test them. We have another shipment coming in of 15 that we call Alpha Plus that fix a few schematic errors that were on this board. There's about 15 of those that exist. Those are the first that kind of go out into the wild. right? They're going to DARPA MTO RIFMLS performers, right? So now once they're in the wild, you have a team of people, and I don't know how many RIFMLS performers might be in the room, there might be a lot. This is the hardware they're using, right? So that's kind of the first foray. That's the first entree to the community at large, right? Now, we are building a substantial number of what we call betas, right? I'm great at naming things. If there's a marketing specialist that wants to come work for me, that'd be fantastic, because I can't name things. A few beta boards coming out early next year, and those go out to a substantial number of government agencies that I have no idea what they're going to do with them. They could potentially contract this community to work on those boards for their projects. Once they have control of those boards, they can subcontract to any one of you to work on those. Another option is potentially to come to BAE Systems and we work out an internal research development project at BAE that you want to use this hardware. Let's do it, right? Come to me, find me, let's do it, right? I can do that. That's within my purview, right? And then after that, the commercial model starts to evolve, right? So have we picked a commercialization vendor yet? We have not. BAE Systems does not sell many commercial modules, right? You don't see a lot of BAE stickers on things that you personally buy. We are working that, and I promise you we are working that. Tom has mandated that we work it, but I don't mean it that way. I want to do it too, right? So I want to get it out there. I can't say a price right now. That's above my purview. I cannot do that. I do know what we sell it to the government for, but I can't even say that. But it's less than a number I threw out earlier. And how much power does it draw? Hey, the engineering answer is that it depends, right? So there's 16 transceivers on this board, and you also have a massive FPGA on the other side. So if you turn absolutely everything on, you're drawing something like 100 watts, 120 watts.
What about the matrix itself?
So the matrix chip itself can draw between 4 watts if you're doing receive only below 6 gigahertz, and 15 watts if you're doing transmit on all 4 frequencies above 20 gigahertz.
That's all up, I guess, right?
Say again?
That's all up with transmit?
Well, much of that is output transmit, right? So down conversion and up conversion in that microwave block is expensive as far as the power consumption goes to get that linearity. So that's also in a high linearity mode. If you're not expecting many blockers or expecting much interference, then you turn some of that down. So there's a wide range, right, of power consumption.
Have you made any considerations for putting it in space?
The answer to that is absolutely, yes, we have. And we are embarking on a project to put it in space in late 2019.
Make it 2.
Okay, all right, sounds good.
Okay. Any other hands? Well, no, the guy behind you was already.
You mentioned that the
I'm sorry, I need to interrupt. The next speaker can please get mic'd up while we do this. Are you already? Okay, good.
You mentioned that the V3 fits in the X310. Where does the V4 fit in?
So the V4, there are no current plans, although we have talked, right? Talk is cheap, but we have talked about making another MEK type of version for the X310. It would just be a respin. I'd have to go back and show you through the slides, a respin of an LCP substrate that we use to mount matrix to the MEK. That's not a huge effort, but nominally V4 is targeting this board, right? So that's, and the other boards that I mentioned but didn't show. That's kind of the future product path for V4. But it's not to say that we can't put it in MEK. There's a small amount of NRE that would need to be closed in order to do that.
I'm sorry, someone else.
Yeah.
There was one there.
Do you have existing like demonstrations that you've done with power amplifiers and antenna circuitries to showcase the full capability of this?
Absolutely. So there's 2 things. Right, so we have sitting up in my office in Merrimack, New Hampshire, a full demo running for a variety of different what I would call DoD-specific modes, like GMTI, narrowband and wideband comms, bistatic radar, those kinds of things. We have a demonstration set up to do that now with this hardware, right? It's not necessarily leveraging GNU Radio for all of those. It's more kind of I would call it just simply more custom demo type of thing. But that type of demo showcases the capabilities of not only the chip, but how you might extend the chip using external things like PAs and LNAs like you mentioned. So I guess the short answer to that is absolutely and yes. It's just not so much leveraging GNU Radio, right? That's something that could be done, right? That's something that I would hope that, I mean, I keep saying it, right, that this community could help me do, but that particular demo doesn't use GNU Radio.
Okay, we have at least 2 more questions, but Raj, can you already start setting up? Ian.
So I walked in a little late, and I apologize if this is a dumb question, but you know, I got the feeling from what you said there that this was very revolutionary from a semiconductor point of view. Is it the sort of thing that is ready to go to mass volume as a semiconductor product, or are there like designed for manufacture things that will have to be solved? You know, you can make things for the military and not address those problems because of the cost they can absorb. Is this the sort of thing that could proliferate very quickly to a commercial consumer price point?
So the MRL of the chip itself is kind of in the 8-9 range. It is made by Jazz Semiconductor, which is a high volume provider. They do 5G stuff, right? So they could print you tomorrow 30,000 versions of this. Where MRL is slightly lagging is in the packaging. Now we have made a package for this thing, right? That's not to say the package that you would want, or that you would want, or that you would want, right? It is a package that does a lot of different things. But when you try to do a lot of different things, you maybe sacrifice the 1 dB of noise figure that you absolutely had to have at C-band, right? Those are the kinds of things that MRL is slightly lagging, right? And then MRL behind that is this board, right? So I'm not building 10,000 of these. When I said I was building a decent quantity in beta, certainly less than 100, right? But those are the type of numbers that my organization within BAE Systems is accustomed to. That's kind of our volume. Our production volume is probably less than NI's, you know, free test samples, right? That kind of thing. But that's not to say that we are finished, right? So this is certainly an ongoing thing. MRL is something that will continue to evolve. But specific to your question, the chip has a very high MRL.
So not related to the hardware at all. I noticed in those screenshots of GNU Radio that you were running it on Windows.
Yes.
Were you using Jeff's unofficial Windows installers, or did you package and install it yourself?
I believe we installed it ourselves, but I'd have to get back to you on that.
Do you want to help us?
I don't know.
Just saying, it'd be a great contribution to the community.
So I will. A bit of a mea culpa is that perhaps, you know, a reason why that's the extent of the demo you saw is that we did have some issues getting GNU Radio working, but I wasn't going to bring that up. Yeah, so I can get you absolutely in touch, and I think we should talk anyway about a myriad things, and potentially that being one of them. So yes,
So you built an RF FPGA, but you weren't able to install GNU Radio on Windows. I think that says a lot about the product. Okay, like, well, already over time, so I'm afraid I'm going to have to, close it out.